Right, in this video, I'm going to be talking to you about semi-log plots, and this is a topic from AP Precalculus that I guess I'll say is not typically part of most people's pre-calculus courses. But I'm excited to show it to you because it's just something different, right? It's not something I had pictured in my mind when I thought I was going to be teaching AP Pre-Cal. Okay, semi-log plots have one axis that is scaled logarithmically, and in this class, it's going to be the vertical axis. Okay, so that's the one that's scaled logarithmically, and really what it means is that each of the main squares, the main grid squares, like we see 1, 10, 100, 1,000, each square represents a power of 10. An exponent that we put on 10 to get 10, 100, 1,000, even 1. Okay, and those exponents are 0, 1, 2, and 3. And that's why it's called a logarithmic scale. Okay, but to give you some more detail on like what this graph or this grid actually is doing, notice at the bottom what looks like the x-axis is actually y equals 1. Okay, and I'm just going to say, okay, that's where we start. Okay, then each tick mark between 1 and 10 represents like 2, 3, 4, 5, 6, and then it gets really crowded up there, so I'm not going to keep writing. But then after 10, 10 to 100 will be steps of 10, 20, 30, 40, 50, 60, 70, 80, 90. But again, it's getting really crowded up there. And then when I plot the numbers between 100 and 1,000, we're going to jump by 100. So 100, 200, 300, 400, 500, and so on. And so you see, okay, the thought was plot the point 1 and 7. So there, I did it. I may have mislabeled the height of that point. I think I did. And so I'm going to go back in and zoom in and make sure that I, was erroneous. But then I'll do the next one first. So plot 3 and 300. So go over to x equals 3, then go up to 100, 200, 300, right there. Okay, that one I'm pretty confident on. Okay, but this one, 1 and 7, okay, I kind of need to think is, okay, this is 1, 2, 3, 4, 5, 6. Okay, it was in the right spot. It was just, so small in there that it looked like it might have been on 6. Okay, so that's the point 1 and 7. All right, and so we've plotted a couple of points on a semi-log plot. And I think that's the first step. Okay, then we're going to want to talk about plotting exponential functions on a log plot, on a semi-log plot. That's going to be really important. That's pretty much the meat of this lesson is what happens when you graph an exponential function on a semi-log plot. So with this table, we can see some patterns. Okay, the first thing I'm noticing is that the x's are evenly spaced, and that's a good thing for us, right? We're going to be able to make judgments. So I'm seeing, to jump from 0 to 1 is an increase of 1, 1 to 2, again, plus 1, plus 1. But then the output values, the values of f, they're multiplying by 5 each time. And that's why I say you don't need regression, right? You can just figure this one out. So we're going to say I multiplied by 5 to get from 6 to 30, did it again to get 150. 150 times 5, that's 750. So we're going to find an equation for f. And I already told you it was exponential, right? In ink on the paper you're looking at. So I know that f of x is a times b to the x. Okay, now, it's been a long time since we've kind of like done this by hand, but I don't really want to use a calculator today. I just don't think it's necessary. Okay, remember that b is that constant multiplier, right? It's that number we're multiplying by each time x increases. And so that's times 5, and x is increasing by 1, so b is going to equal 5. And then a, we can find that with f of 0. That was something we learned earlier in the course, is that f of 0 is just going to be that beginning, because b to the 0 is going to equal 1 for any non-zero b. But if b was equal to 0, the function would be 0 everywhere, and that wouldn't be all that interesting in the first place, so that's why we say we're not interested in the 0 base. A is f of 0. F of 0 is 6 from the table. I've got a times b to the x. That's going to be 6 times 5 to the x. Okay, so I've got that. It's ready to go. Now we're going to plot the data on the semi-log plot. So I'm going to plot the point 0 and 6. And then I'm going to plot the point 1 and 30. And then I'll plot the point 2 and 150. And then I'll finish up graphing 3 and 750 right there. It's like, oh, I see something here. If we look, these points are all lined up. Okay, so we're seeing, up to my ability to draw a straight line that happens to pass through all of them and plot them accurately, we've got ourselves, something that looks like a linear pattern. And that's pretty much the main piece of knowledge I need you to get from this lesson today, is that when we graph an exponential function on a semi-log plot where the vertical axis is logarithmically scaled, we should see a linear pattern. But why does this work? What's going on here? That's where I'm going to go in and show you algebraically what's happening. So I'm going to just look at this as y equals 6 times 5 to the x. Okay? And then what we did to the y-axis, really, when we turned it into this semi-log plot, is we took the log with base 10 of the y-axis. Okay? And so I'm going to take log base 10 of both sides of this equation, because if y is equal to 6 times 5 to the x, then log base 10 of y should equal log base 10 of 6 times 5 to the x. But I'm going to be using some logarithm properties that we haven't talked about for a while in this class, but you still need to know. Okay, just for situations like this, I need you to remember that when we have multiplication on the inside of a logarithm, that can turn into addition of logs. Okay? So I'm going to split up that log base 10 of 6 times 5 to the x into log base 10 of 6 plus log base 10 of 5 to the x, okay, with that addition. But then I need you to remember another property, right? That exponent on the argument of a logarithm, we can work with that. Okay, log base p of u to the p is just that power p multiplied by log base b of u. Okay, and I proved that for you, long ago, last semester. And but if you're interested, it's still there. You could go back and look, and you could see me prove it for you again if you were feeling like some doubt about these properties. But either way, I'm just going to swing that x around the front and say that log base 10 of y equals log base 10 of 6 plus x times log base 10 of 5. Now, I don't think that this exactly shows you exactly what I want you to see in the way I want you to see it. So I'm just going to rearrange some stuff. If 4 plus 3 is the same as 3 plus 4, I should be able to add the thing with the x to the thing without the x, or the other way around. So I'm just going to switch the order in which they're added, and then also, just put the constant in front of the x, so that hopefully maybe you see what I'm kind of getting at here with the linear pattern. That log base 10 of y is a linear function of x. Okay, it's mx plus b, where m and b are just, some weird numbers that we definitely weren't familiar with in Algebra 1, but it does go all the way back to Algebra 1, the concept of y equals mx plus b, what we're doing here. Right, and that really is the main message. So here you see it's one of our AP Precalculus essential knowledges. When the y-axis of a semi-log plot is logarithmically scaled, data or functions that demonstrate exponential characteristics will appear linear when graphed on that semi-log plot. That's the message. You need to hear it, and it goes both ways. If you see a semi-log plot and the data appears linear, you're working with an exponential situation. And if you're already working with an exponential situation and you go to plot it on a semi-log plot, it should appear linear. All right, so we're going to sketch some graphs. 10 times 2 to the x and 3 times 10 to the x. And just like any time when we're getting started graphing new types of functions or on new types of grids, we should probably make a table, plot points, connect the dots, right? So we're going to sketch the graph of f and g, and I'm just going to make the table for both of them like immediately, and then plot the points and connect the dots after that. Okay, I know that these should both form linear looking graphs on the semi-log plot. All right, so when x equals 0, I'm going to do f of x first. 10 times 2 to the 0, that's going to be 2. No, that's going to be 10, right? 2 to the 0 is 1, 10 times 1 is 10. Yeah, okay. Then it's going to be 10 times 2 to the first. That'll be 20. Okay? And each time x increases by 1, output will double, right? That's that 2 to the x pattern. So 40, 80, 160, 320. Okay? But then for g, I'm going to be thinking, okay, 10 to the 0 is 1. So this one's going to start at 3. Once again, we're seeing that f of 0 or g of 0 being the a and the a times b to the x. Okay, but then each time x increases by 1, output should increase by a factor of 10. It should multiply by 10. So I should go 3, 30, 300, 3,000, 30,000, 300,000. But this scale only goes up to 1,000, right? So even 3,000 I'm not going to be able to plot. I'm not going to try to extend the grid or anything. There's a message here. Okay, so first I'm going to plot this one 0, 10. Okay, then 1, 20. 2, 40, 20, 30, 40 right there. 3 is 80, so that'd just be short of 100 by 2 marks. 4 is going to be 160, which is going to be, between 100 and 200. And we don't have to be too fine if they don't give us grid in there. It's probably closer to 200 than 100 on the logarithmic scale, but don't even worry about that. I already recorded the video, the homework. I ran into a situation like that. I think I gave that enough discussion there. That'll be, leave that there. Okay, then 5 is 320, 100, 200, 320 should be about like that. And yes, we are seeing that, that linear pattern. Okay, I'm going to draw a line since this is a perfectly exponential function, they should have lined up perfectly. I didn't graph it perfectly because we are humans and we do not graph perfectly. If we want a perfect graph, we're going to go open a browser window and type in Desmos.com, right? That's going to be the best way. Okay, but then I've got, like I said, there's a message here. So 0 and 3 would be there. 1 and 30, 10, 20, 30. 2 and 300, 100, 200, 300 here. Okay, and then I go off the graph, so I'm just gonna kind of connect these dots, let it snap to. That looks pretty good, and it makes sense that this would be more linear because I actually was able to go off the grid. Okay, but what I'm saying is that I've got a steeper slope on the right than I have on the left, and that difference in slope is caused by the difference in the growth rate. Okay. The g of x has a steeper slope when graphed on the semi-log plot because it's got a bigger growth factor, right? And f has a smaller growth factor. So I'm seeing, okay, where is it? Okay, yeah, 10 to the x, that's a very fast growing function, right? Big growth factor, much bigger than, say, 2 to the x, okay? And so that's why I've got a steeper slope, okay? I think that's enough on that. We'll have more to say about this. With the next set of examples, I don't want you to worry too much about like the actual input output, like the table. I'm just going to show you what the table is for these. I kind of had a change of heart. And also I want this video to go by as quick as possible because it's supposed to be a quick and easy lesson. I want it to be a quick and easy video. All right, so I'm showing you what like a table of inputs and outputs for both of these functions. What I want you to see is that the output is decreasing. This is exponential decay, right? That 5 to the negative x, remember we can write that as 5 to the negative 1 to the x power, and 5 to the negative 1, 1 over 5. So if I plot 0, 1000 here, and then I plot 1, 200, 2, 40, 10, 20, 30, 40, and 3 with 8, I'm seeing that same linear pattern. This is great. But because it's exponential decay, I should be seeing a negative slope on my line. Okay, let's do that again and see if we get the same thing over here. 0 and 256, 100, 256, I'm just going to think that's about there. 1 and 64, 10, 20, 30, 40, 50, 64. Then 2 is 16. So it'd be between 10 and 20. Now, that's, again, you'll see more on the homework on this. 16 is actually going to be quite a bit closer to 20 than it is to 10, but I don't really want to talk about that. That doesn't seem like that's really part of the AP Pre-Cal course. And then 3 and 4 is 1, 2, 3, 4 right here. Okay, another one where we've got a downward sloping linear pattern that means that I'm looking at exponential decay. Also, looking at the slopes of these, they look very similar. And that's because the growth rates are very similar. 1/5 to the x versus 1/4 to the x, right? Those are similar numbers. 0.25 and 0.2, also very similar numbers. We're seeing similar slopes. Okay, and really that's all. So if you were just here for like what I must know for this lesson, I think you can probably move on and start doing the homework. But I'm going to do some more examples here. Remember from last semester that a data set shows an exponential pattern if output values have a constant ratio when input values are evenly spaced. So what value of k would make f an exponential function? Well, exponential is 6 times r equals k. And then 6 times r would get me all the way to 24, right? Yeah, well, where r is probably the 4th power of the actual value of b or whatever, so I'm glad I called it r. 6r squared equals 24. Wait a second, I can solve that for r. R squared equals 24 divided by 6 is 4, and that must mean r is equal to 2. Now, if r was -2, we don't really deal in like -2 to the x. That's not really it's a function, but it's a really poorly behaved function. If you're interested, go graph -2 to the x on Desmos and see that it's continuous nowhere. It's really, really a bad function. And so then, so I've got r equals 2. So if I multiplied by 2 each time, if k equaled 12, right, 6 times 2 equals k, that'd be k equals 12, would make exponential. Okay, 6, 12, 24, that makes a lot of sense. Constant multiplier. Okay, but if we want it to be linear, we need to just increase by the same amount each time. 6 plus, I guess maybe I'll call it delta x equals k. And then 6 plus 2 delta x's, or maybe it's delta y. Yeah, pardon me. Error. That's going to equal 24. So I'm going to subtract 6 from both sides and get 18. And then change in y would be 9. So 6 plus 9 is 15, and 9 plus 15 is 24. So k equals 15 would give me a linear pattern. And that's something we're going to need to talk about in a few days, the difference between exponential and linear, because that's one of the topics I just kind of conveniently forgot to show you about throughout the year. Okay, recall also that an exponential function with a vertical translation may not have a constant ratio in its output values, but we sometimes can add or subtract a constant to undo that, and we see that constant ratio pattern. I'm just going to show you A, because B and C, they're pretty easy to find as well, and this is a very fringe topic here, but it is one of our essential knowledges. So 7, 13, 25, 49. Oh, I'm thinking, maybe 8, 14, 26. Wait a second, I'm not really seeing a pattern there. But this is near good numbers. Maybe I subtract 1. 6, 12, 24, 48, 96. There it is. All right, so f minus 1 makes 6, 12, 24, 48, and 96. And that is an exponential pattern. That's not like f inverse. That's like f of x subtract 1. I'm just going to do the subtraction and see that constant ratio. I'm going to sketch the graph of y equals x once again. 0 and 7. Okay, so 0 and 7 right there. 1 and 13. Okay, that should be about there. 2 and 25. 3 and 49 is basically 50. 20, 30, 40, 50. And 4 and 97, that might as well be 100, just a little bit underneath it. And look, the data are still forming a linear pattern. And you can see that fact kind of peeking out from the bottom. One advantage of semi-log plots is that a constant never needs to be added to the dependent variable values to reveal that an exponential model is appropriate. And just the thing is, not all that often are we presented with, here's a semi-log plot for you to sketch on and see if the points line up, right? But I just did want to show you that because that's definitely something it's an essential knowledge. They determined it was essential for you to know that, so I want you to know it. All right, and then there's also this situation where we have like a table where instead of input, output, we've got input and log of output. Now, this is another fact. If both x and log base b of y for any suitable base b, where basically b is a positive number and not equal to 1, if they both form a linear pattern, then y is going to be an exponential function of f. On a vocabulary level, sometimes people will call a linear pattern an arithmetic sequence. That is vocabulary you need to know, but I'm going to come back and do a follow-up video, or a few videos on topics I just conveniently forgot about or just skipped over for convenience. One of them is going to be sequences. We'll talk about arithmetic and geometric sequences then. All right, but for now, we'll just call it a linear pattern. I've been calling it that this whole video. So what value of k would make f an exponential function? Okay, I just need to see a linear pattern between x and f of, like on the values here, plus 2, plus 2, plus 2, that's good, plus 0.4, and then this went up by plus 0.8, so I must be needing to go up by 0.4 each time, so k equals 1.5. All right, and then the last two examples I've got are, honestly, these are kind of the level that the AP Calculus or AP Pre-Calc questions I've seen about semi-log plots are working on. It's not that advanced, okay? Here's a semi-log plot, here's some data, you see they line up, therefore it must be an exponential function. So get rid of anything that's not exponential. Those are not exponential. Okay, now it could be either of these, so I'm just going to start plugging in values. I'm going to plug in t equals 0. P of 0 needs to equal 2. Okay, but when I plug in 0 in there, I'm going to get 2 plus 1, which is 3, so that one's out as well, and I know that answer choice D is the correct one. Right? And then on the other one, which of these figures is the graph of f on a semi-log plot? Okay, and I've seen other ones like this. Some of the answer choices aren't even graphed on a semi-log plot. So I'm getting rid of A and C. These are not semi-log plots. Just get those out of there, right? Because it said it had to be on a semi-log plot. And then let's look at the output values. 40, 60, 90, 135, 203. These are numbers that are definitely bigger than 10. Okay, so B is going to be out as well because all of those output values are much smaller than 10. Okay, so then I'm saying, yeah, 40, 60, yeah, something between 10 and 100. 90, very close to 100. 135, bigger than 100. And then 203, between 100 and 1,000. Okay, so that's why I'm going to be choosing answer choice D. That's all I got for this video. Thanks for watching.